Good morning. Today we are going to continue with our investigation of electricity. Now we'll be looking at circuits and specifically two types of circuits called a series and a parallel circuit. So let's commence operations. This device is called a multimeter. It's called a multimeter because it could measure several different quantities involving electricity. The dial is pointed at 20 here, and this means it could measure a voltage of up to 20 volts. However, if you have the dial pointed in this area, notice it says an A here, that area is used to measure current. And finally, if the dial is aimed somewhere in this area, notice the symbol here, it looks like an ohm, and it is indeed an ohm. This particular area of the multimeter can measure resistance. So this area measures voltage because there's a V there. This area measures current with the A, and this area can measure resistance with the ohm. So now on to circuits. To understand circuits, we need to understand some laws that were derived by Kirchhoff. So let's start off by looking at Kirchhoff's current law. The total amount of current, or electrons, into a junction point of a circuit equals the total current, or electrons, that flow out of that same junction. So let's look at figure 1a. Imagine we had 10 electrons moving. And these 10 electrons hit this specific point called a junction. A junction is where one path becomes more than one path. In this case, two paths. One path going in this direction and one path going in that direction. That's what a junction is. And so these electrons, for the sake of argument, we'll say they're flowing east. Notice we have two electrons that move in this direction. So the question is, how many electrons have to head here? Well, if we look at Kirchhoff's current law, it gives us the answer. The total amount of current or electrons into a junction point of a circuit equals the total current or electrons that flow out of that same junction. So, if we have 10 going in and 2 travel along this path, then 8 have to travel along that path. And finally, 10 electrons continue to make their journey in this direction. That's Kirchhoff's current law. It basically says that electrons can't be created nor destroyed in a circuit. Just keep that in mind. The same goes with current, because current is just a measure of electron flow over time. So again, we have 5 amperes. For the sake of argument, we'll say traveling east. And if 1 ampere flows in this load called atarax, then 4 amps have to flow in this load called JGS. Just like electron number added, so does current. 4 amps plus 1 amp has to equal 5 amps. And ultimately at this point, there is also 5 amps. So similarly, as electron number has to add up to 10 in this case, 4 plus 1 has to equal 5. These are the laws that Kirchhoff came up with in relation to current. Which resistor, JGS versus atarax, has more resistance? So think about that for a moment. 5 amps came in, 4 amps went across load JGS or resistor JGS, 1 amp went across the load named atarax. Which one has more resistance? Did you think about it? Did you? I hope you did. It's the atarax load that has more resistance. It has to be because remember that the greater the resistance, the less the current. Since atarax has less current, that must mean it has more resistance. Now Kirchhoff also came up with a law related to voltage, or potential difference. The total of all electrical potential differences in any complete circuit loop is equal to any potential increases in that circuit loop. So what does that mean? First of all, what does a circuit loop mean? And what does a potential increase and a potential decrease mean? Well, for the sake of argument, let's say that this specific cell or battery has a voltage of 20 volts. Voltage would be increasing here, or potential would be increasing because that's what a battery does. It adds energy to the circuit. Now, we will assume that these wires are perfect conductors and that they have no resistance. So we'll assume that this wire has 0 volts. The switch we'll also assume has 0 volts. This wire we'll assume also has 0 volts. And this last wire connecting we'll assume has 0 volts. And so what Kirchhoff's law basically says is this. If we have 20 volts at this point, then at this same point where instead of there being an increase in potential, there's a decrease in potential because the electrons are transferring their energy to the load, it basically says that 20 volts has to equal 20 volts. That's all it says. But let's for a moment assume that the wires aren't perfect conductors, that the wires have a little bit of resistance, so as a result they'll have a small amount of voltage. So let's assume for a moment that the electrons gain energy at this point, their voltage is 20 volts, but then there's a little bit of voltage loss here, and then the switch, some more voltage loss. Then there's some more voltage loss here along this wire, and a little bit more voltage loss there along that wire. I want you to pause the video right now, but the question I have for you is, what do you think the voltage of this load will be? All right, I hope you gave it some thought. The voltage will be 19.96. In other words, if there's some voltage loss in the electrons as they make their way to the load, that load then cannot have 20 volts. It's going to have less than that. All right, let's look at another example here. So once again, we will assume that the wires in the switch have 0 volts. In other words, they have no resistance. They're perfect conductors. So we know that this is 9 volts and this load has 2 volts. I want you to pause the video right now and I want you to consider what you think this question mark will be. In other words, what you think the voltage of this load will be. But let's read this one more time. The total of all electric potential decreases, the total. This is where the decreases are happening, here and there. The total of all electrical potential decreases in any complete circuit loop is equal to any potential increases. Here's the increase. And there's only one battery. Here's the decreases. How much does this have to be? Pause video now. Okay, I hope you tried this example. So we'll call that V2. And I think it's important whenever you work on these problems that you draw a path. So please draw the exact same path I just did. The path always starts at the battery and goes from the positive terminal to the negative terminal. This is called a complete circuit loop when it comes back to where it started. So that's what we mean by the term complete circuit loop. Your loop starts here and goes all the way around. All right, so we start off with the battery. It's just easier if you do that. So we start off with the battery, we write Vt equals, because this is our potential increases. And what's it equal to? all the electric potential decreases. So VT equals. Now as we go along this path, the first load we hit where there's a decrease in potential is V2. So we write VT equals V2. And we continue along this path, and now we hit this load here, which is called V1. So VT equals V2 plus V1. Or 9 equals V2 plus 2. And doing some math, we end up with 7 volts. 2 plus 7 has to equal 9, so long as these voltages are 0. Now the circuit we just looked at is called a series circuit. So let's explore this in great detail now. Current, or the electrons, in a series circuit only have one path to travel around the circuit. So that's the definition of a series circuit. We only have one path. There's no junctions. Solve the current given the following circuit. So that's our goal, to try to get the current. Let's see how we do this. So once again, we draw our complete loop. Starts at the battery, goes from the positive terminal all the way around back to the negative terminal. And we start off by writing VT equals. So we started our battery. VT equals. The first load as we go along this path that we've just crossed through is V2. Second load is V1. All the potential difference increases have to equal all the potential difference decreases. VT equals V2 plus V1. Or 10, which is our VT, equals V2 plus V1. Now here's the problem. We're not told V1 or V2, but we do have a formula. Recall this formula, V equals IR. So we're going to substitute this formula into this equation. So now, what does it become? 10 equals, well, V2 would become I2 R2, and V1 would become I1 R1. Now we know the resistance of this load, it's 2 ohms, that's why we've written 2 here. And we know the resistance of this load, that's 3. And it looks like we're stuck because we have one equation and 2 unknowns. But in a moment you'll see we're really not stuck at all. Here's the one definition of a series circuit that you need to be aware of. Current is the same everywhere. So I know right now we wrote I2 and I1. When you write that, it's almost like you're saying there are 2 different currents. One through load 1 and one through load 2. But that's not true at all. Current is the same everywhere. And so instead of writing I2 or I1, we could just write I. And now we have one equation and one unknown. And so 10 is equal to I times 2 plus I times 3. Or we could rewrite that as 10 equals 5I. 2 plus 3 is 5. And then dividing by 5, I is equal to 2 amps. Now going back to the circuit and solving for the voltages to see if the answer makes sense. V is equal to I times R. 2 times 2, that's 4 volts. So the voltage of load 2 is 4 volts. Once again, using the same formula, V equals IR. 2 times 3 is 6 volts. And so going back and labeling this, do these numbers make sense? This is a way of checking your work. Well, 10 volts is here, And 10 volts is indeed equal to 4 plus 6. So it makes sense. The second type of circuit we're going to explore right now is called a parallel circuit. The main difference between a parallel and series circuit is that for a parallel circuit, it has a junction. In other words, there are more than one path. And looking at this circuit, it actually has two paths. There's a junction here where the current will split, and there's a junction here. And so let's begin our path. Current leaves the positive terminal, and as soon as it hits this point, it's going to go two different ways, because that point is called the junction. So it's going to go through load 1 and then through load 2. We're going to call the current through load 1 I1 and the current through load 2 I2. This time you're going to see in a moment the currents are not the same. They'll actually be different. They may be the same in one specific case, but most of the times they will be different. I'd like you, when you draw your diagram, to color code it like I have. Ensure that you have 3 different colors. It doesn't matter which colors you choose, but ensure there are 3 different colors. Now, the current coming from the battery, in some textbooks you may see the symbol IB. In other textbooks you may see IS, IB standing for current of the battery, IS standing for current of the source. In other textbooks you may see IT, T standing for total current. We'll use the symbol IS, but it doesn't matter which symbol you use. It could be the power from a nuclear power station, it could be the power from a battery. So the question is, how are I1, I2, and IS related? How is this variable, that variable, and this variable, how are they all connected together? Well, recall that when electrons or current hit a junction, it adds. 1 plus 4 is 5. 2 plus 8 is 10. And so similarly, IS is equal to I1 plus I2. IS is equal to I1 plus I2. You need to memorize that for a parallel circuit. Next question is, how are the voltages related? How is the voltage of this load related to the voltage of this load related to the voltage of the battery or the source? Well, we're going to look at the first path here, because now there's just not one path, there are 2 paths to take. And so starting off with the battery, we work our way around and we hit V1 or load 1. So we would write Vs equals V1. Notice for this first path, we're only hitting one of the loads. Follow my hand as I go around this path. We hit one battery, which is called Vs. That's this side of the equation. And then we hit one load, which we call V1. Now we're going to look at the other path here. Again, start here at the source. I'm going to go around one more time. So at the source, we write Vs. Now we're going around, and we're going to hit this load, which is V2. And that's the only other load we're going to hit. Here, the electrons gain energy. Here, the electrons transfer their energy to the load. That's why we're writing Vs equals V2. And so how are they all related? Well, if Vs is equal to V1 and Vs is equal to V2, then Vs is equal to V1, which is equal to V2. In other words, the voltages in a parallel circuit are always going to be equal. So these are formulas that you have to keep in mind for parallel circuits, which make them unique or different from a series circuit. Finally, the last topic I want to look at is something called equivalent resistance. This is a measure of the overall resistance in a circuit. And so for a series circuit, here's the formula for equivalent resistance. We normally denote it with an RT or RS. RT is equal to R1 plus R2. If there was a third resistor, it would be R3 plus R4 plus R5, depending on how many resistors you have. But notice as you add more and more resistors, you get a bigger equivalent resistance. So for this situation, it would be 5 ohms. 3 plus 2 is 5. Now why is this helpful? Well, if we have the equivalent resistance, it's helpful to determine the actual current. What do I mean by that? Well, to get the current in the circuit, all we have to do is divide the voltage by the resistance. So the voltage was 10 volts. The equivalent resistance is 5 ohms and it's 2 amps. Now, if you recall, we had to do all this work previously to get 2 amps. Now, all we have to do is use this formula, and that's it. So you don't have to do all this work to get 2 amps. Now just use the equivalent resistance to get the 2 amps. So it's almost like a shortcut. Once you know the formula for equivalent resistance, you no longer have to do all this work that you just did a few moments ago. You just take the overall voltage, divide by the equivalent resistance, and you get the same answer. Now let's look at the equivalent resistance for a parallel circuit.